Assalamualaikum warahmatullahi wabarakatuh. So today we will continue a new chapter, which is chapter 5, Z Transform. So for this chapter, we will divide into 6 parts, which is the first part is introduction, continue with part 2, which is method 1, to find the Z transform by using the definition. And then for the part 3, we will see how to find the region of convergence, or ROC, for two types of signal, infinite and the finite signal. And part 4, we will continue with the method 2 to find the Z transform by using the properties. And lastly, for part 5 and part 6, we will see the inverse Z transform, which is for the inverse Z transform, we have 3 methods: long division method, partial fraction, and also the residue method. And for the part 6, we have 3 applications for the Z transform, to find the transfer function, to find the stability, and also the network realization. Okay, let's see the first part, which is introduction. So for the discrete signal, this one, the analysis of any sample signal or sample data signal, which refer to the discrete signal. When we do the analysis by using the Laplace transform, it will have infinite long polynomials due to the characteristic of infinite number of poles and zeros. So that's why we use the Z transform to reduce the poles and zero. When we use the Z transform, we will map the Laplace into the Z plane, where we have the radius and the angle of the signal. So in the Z transform, we will represent it with exponent st. So s refer to the sigma plus minus j omega. Okay. So if we change the z into z negative n, so previously we have z exponent st, so z negative n will be equals to exponent negative nst, like this one. So the important part is we have the equation for Z transform here. So we will see after this the definition of Z transform. So for introduction, to find the Z transform, we will have the summation of 0 until infinite signal of xn multiplied with z negative n. Okay, so in this slide, the important part is the purpose, or what is the usage of the Z transform. So we can see here, by using the Z transform, we can find the transfer function, the stability, and also the digital network realization. So we will cover this part at the end of the Z transform chapter. This is the figure of Z plane. So for the Z plane, we will represent our signal with the radius r and the angle of omega. Okay, so as you can see here, for the Z plane, we have the real value of Z and also the imaginary value of Z. So for the real, we will plot at the x-axis, whereas for the imaginary signal, we will plot at the y-axis. Okay, next is part 2, which is we need to find the Z transform by using the first method, or by using the definition. So as we can see here, this is the general equation for the Z transform. So when we need to find the Z transform by using the definition, it means that we need to use the formula of Z transform. So this is the general equation, where the limit is from negative infinite until infinite, the summation of xn multiplied with z negative n. For the general equation, we will use the non-causal signal, where the non-causal is the two-sided Z transform. And we can also use the Z transform for only one-sided Z transform. So for one-sided, we have causal and anti-causal signal. We can represent the causal with this graphic, where we have the signal for the xn is always 0 for n lower than 0, which means that at the negative side we will always have the value of 0, whereas for the positive side we will have value. So this is the causal signal. Okay, for the causal signal we have the signal from n equals to 0 until infinite, xn multiplied with z negative n. So what is the difference of anti-causal signal? So we can see here for the anti-causal, the value of xn will equal to 0 for n larger than 0 and equal to 0. So we can see here at n equals to 0 and larger than 0, which is the positive side, the value will always be 0. And we have the signal, or we have the value at the negative side. So this is the anti-causal signal. So for the limit, it changed from negative infinite. So we have the summation of n equals to negative infinite until n equals to negative 1 of xn multiplied with z negative n. So this is the one-sided signal of anti-causal signal. Okay. So this is the equation that you need to memorize to find the Z transform by using the definition. So let's see the first example, example 5.1. We need to determine the Z transform for the analog input signal xt. So we are given the analog signal. This signal is applied to a digital filter. So first of all, when we have the analog signal, we need to change into the discrete signal, and then only we can transform it into Z transform. So first we need to change the analog signal into the discrete signal, where for the transformation we have studied during the sampling chapter. So the T will be changed into NTS. First we need to transform the analog signal into the discrete signal, where we have xt equals to exponent negative at. Okay, so to transform to discrete signal, we need to change the t into nts. Okay, or in this case we represent the ts as the capital T. Alright, so our x nts will be equals to exponent negative a and capital T. Okay, so this is our equation. We need to change the value of n. For example, if we consider the case for the causal, for n equals to 0 until infinite. Okay, so for this case, so we will have the discrete signal xn. So nts will equal to xn. So this one will be equals to exponent. We need to change the value of n for n equals to 0 until infinite. So we will get the list of xn. For the first one, we change to n equals to 0. So we have exponent 0. And then when n equals to 1, we will have exponent negative a capital T. And then when we have n equals to 2, we have exponent negative 2at. And the list will be continued until n equals to infinity. So we will get this list of signal. Okay, so the marker will be at exponent negative 0, or for exponent negative 0 is equal to 1. So we will get this list. So next is we need to find the Z transform for the discrete signal that we have calculated previously. We use this one-sided Z Z transform for the causal. So this one will be equals to, first one we have x at n equals to 0, which is the value is 1, multiply with z negative, so n equals to 0. And then the summation means we have the plus here for every list in the discrete signal. I forgot to put the marker here. So next is at n equals to 1, we have exponent negative at, and now it will multiply with z negative at n equals to 1, and then plus exponent negative 2at, this one, exponent negative 2at, multiply with z negative at n equals to 2. And the list will continue until infinite. Okay, so we will have 1 plus exponent negative 80 z negative 1 plus with exponent negative 280 z negative 2 plus until infinite. So this one until infinite. Alright, so for the infinite summation, we can use this equation to simplify the summation of the signal, where we have the summation for k equals to 0 until infinite. Alpha k will be equals to 1 over 1 minus alpha. So in this case, we change our equation into this form. So we have the equation for Z transform, summation for n equals to 0 until infinite. Okay, xn is exponent negative a and t, capital T, multiply with z negative n. Okay, so we need to simplify this equation into the summation of n equals to 0 until infinite. And then we factorize the power of n here, so that our equation will be in the form of alpha k. So we have exponent negative a capital T multiply with z negative 1. And this one will be to the power of n. Okay, when we expand this power, we will get the previous equation, which is exponent negative a and t multiply with z negative n. So this is our alpha. Okay, so this k is we change to n. Okay, so this one will be equals to, so in this case our alpha will be equals to exponent negative a capital T multiply with z negative 1. So we have 1 minus exponent negative a capital T z negative 1. Okay, so this one we can also change to the positive power of z. This one we have z with the negative power, so we can change into positive power by multiplying with z over z. So z divided by z is 1. So now we can expand this equation. It will have z divided by, so z multiply with 1 minus exponent negative a capital T z negative 1 will be equals to z minus exponent negative a capital T. So this is the answer for the Z transform of the given analog signal.